Hi Chem 2, this is Dr. Ricardo. This is the second video for Chapter 17. This video is going to concentrate on one topic, and that is titrations. So I'm going to show you the setup first, and then we're going to talk about the different kinds of titrations that you can do and what you should expect, and the calculations that go with them. So the typical setup for a titration in the lab is that you have a beaker at the bottom where you put a particular acid or base that you're studying. So in this particular case, we're putting a concentration of HCl, and we don't know what its concentration is, but what we do know is we know what its volume is, because you can always measure the volume of something. Okay, so if we want to figure out what the concentration of this HCl is, what we can do is we can put it in the beaker. We put a stir bar on the bottom. This is a magnetic stir, right? We're not going to heat it up. We're just going to keep it mixing. So once I turn this knob here, it's going to create a magnetic field that alternates, and the magnetic stir bar is going to zip around in a circle, and you've seen that before. So you want to keep the solution constantly moving. All of these reactions between the base and the acid are going to occur very quickly, okay? So on the order of a second, and the whole thing will come to the new pH. So the reactions are all very quick. So as soon as the pH meter stabilizes, you can write down the reading. Okay, so we calibrate the pH meter, we attach the probe, so this is the pH probe, and it's going to be sitting right in the beaker. Okay, usually you have to hold it with another clamp or something like that, but since this is just an artist rendition, you don't even have to show that. Okay, so what's up here is, this is called a burette. We fill the burette with a known concentration of sodium hydroxide, so we can measure what volume of sodium hydroxide we're adding. And since we know its concentration, we can calculate the number of moles that have been added. Okay? All right, so instead of putting an indicator, we're going to monitor the reaction with the pH meter. Okay? So before I add any sodium hydroxide, this thing is just completely filled up. Let's say this line right here reads 0, right? Burettes go opposite. They're going to read 0 at the top, and when you deliver all of the liquid down here, it's going to read 50 down at the bottom if this was a 50 milliliter burette. So if you take it from 0 and you go all the way to 50, how much has been added down here is 50. If you take it from 0 and let's say it only goes down to the 10 line, then 10 is missing from here. Where did it go? It went down into here. So the reading actually doesn't measure what's in here. It measures how much has been delivered, okay, which is what you need. Okay, so before I add any sodium hydroxide, this thing has a very low pH. This is a little hard for you guys to see, but it's pH, let's see if I do this, it's pH 1.5, right? Can you guys see that? 1.5, okay, very low, right? All right, I start to add the sodium hydroxide, open up the nozzle, right? They call it a stopcock. Drop some in, stop it, write down the pH. After I add a certain number of milliliters, it goes up to pH 3. Then it goes up to pH 4, then it goes up to pH 5, all very, very slowly. I'm adding a fair amount of base, and the pH is barely moving. Then all of a sudden I come close to something called the end point. The end point is when I've added the correct amount of moles of sodium hydroxide to neutralize the moles of HCl. So I'm to the point where I've added an equal molar amount of sodium hydroxide that's comparative to the amount of HCl that was originally in here. Then all of a sudden the pH is going to start to take off. It's going to go to 5, 6, 7. And our expectation in this case is that the end point, right, the steepest part of the titration curve will be at pH 7, because right at that point, I've neutralized all of the acid with base, and really all I have is a solution of water, which is the product of OH and H, and a small amount of salt in it. And NaCl should not cause the solution to have any extra hydronium ions or any extra hydroxide ions. So I'm expecting the pH at the end point to be 7. Okay, well, let's take a look at the typical pH curve. So this is the setup, and this is the graph that you're going to see or create. So in all of these, you measure on the y-axis, the dependent variable, what the pH is, okay? On the x-axis, you measure how many milliliters of sodium hydroxide has been delivered from the burette, okay? It's been delivered from the burette. So if we went and did this experiment, we would get experimental points all along the way. What is the pH after I add 10 milliliters? What is the pH after I add 20? What is the pH after I add 30? What is the pH after I add 40? Look at that. All of those readings, even though I've added 40 milliliters, I'm still under pH 2. I started at pH 1.5. Then gets interesting, right? Once I start to get close to the exhausting all of the acid that's in the solution, now my pH quickly takes off. So if I did like 41 milliliters and wrote down the answer, 42, 43, 44, 46, 47, now I'm starting to get a lot of action. And then all of a sudden, boom, the pH will jump up. So you can go pretty quickly over here and open the stopcock and add a fair amount of liquid. But as you get close to the end point, and how do you know you're getting close to the end point? Because the pH starts to change. As I get close to the end point, I'm almost adding it drop by drop. And then, bam, look at that. I go through the end point, right? From here to here, it might be a total of like 4 or 5 drops from seeing it at pH 2. Then, all of a sudden, 4 drops later, it'll be up here at pH 10.2. Then it starts to slow down again, because after that, really all I'm doing is adding sodium hydroxide to salt water. So it's just getting diluted. It'll keep on going up very slowly over here, but this is an unbuffered solution, pretty much like it was down here. So strong acid, strong base, I expect it to be very flat initially, super sharp endpoint, and then very flat again. That's my expectation. And I'm always graphing versus the number of milliliters of whatever is in the burette. So in this case, I'm titrating the strong acid HCl with the strong acid sodium hydroxide. My very special point, the point when the moles of acid have been totally neutralized by the moles of base, is 50 milliliters. And the pH of that solution, the pH of all solutions that occur at the end point of the titration of a strong acid with a strong base, is pH 7. Okay. All right, so that being said, let me just move the camera out a little bit. Let's go through the notes. So this is acid-base titrations. How's that? So acid-base titration curve is a plot of the pH of a solution of the acid or base against the volume of the added base or acid that's added. In our case, we did the titration of a strong acid, that's what goes in the beaker at the bottom, with a strong base. So over here is the strong base, so we expect our titration curve to look like this, where this is milliliters of sodium hydroxide added. So I'm adding NaOH and my pH is going to go up. Okay? So the sodium hydroxide, the thing I'm doing the titration with, the known concentration goes in the burette. What goes down here? The unknown concentration of the acid. All right. The other kind of titration you can do is the titration of an unknown base. So the base goes down in the bottom. Here's B. I don't know what it is. I don't know what its concentration is. And I put a strong acid in it. Okay? And I'm slowly adding this. So this is added acid. I'm adding HCl. And usually I would do a titration always with a strong base or a strong acid. So here goes HCl, and it's going to get added to the base. Well, what would we expect in this case? Well, a base, before, if I was measuring the pH, right, I got a pH electrode in here. Let's go into the pH meter. Same thing over here. Go into the pH meter. This one I would expect, before I add any acid, the pH is going to be high. then it's going to drop off very sharply and go to that. So this is the pH that I would expect here for the titration of a acid, weak or strong, especially strong because that's what makes it so sharp, versus NaOH. And here, the titration of a base versus HCl, I'm expecting the pH to drop down. Okay? This is low pH, this is high pH. Same here, 0 to 14. Okay, so that's our expectation. Most of the time we're doing these kind. Okay, and here's our special point, right? The sharpest slope is called the endpoint. You want to know how much sodium hydroxide it takes to reach this special point called the endpoint, because that will help you calculate what the concentration of the HCl is. It's a special place where the moles of acid are equal to the moles of base that have been added, because they knock each other out, they neutralize each other. Same thing here. This is the special point, this number of milliliters of HCl, because it will help you calculate what the concentration of this base is, right? The stronger the base, the further along it's going to take before it breaks. Okay, so what are our different situations? So the situations are strong acid versus strong base is the one we just talked about. The equivalence point is the point in the titration where the stoichiometric amount of reactants have been added. So if I have a strong acid, strong base, I'm going to add the same number of moles of acid to the base or base to the acid, depending on which kind of titration I'm doing. And anytime I want to know the moles of something, you can use this kind of neat little formula, right? So at the end point, right, this is always true, at the end point, a very special place where the moles of acid are equal to the moles of base. That will always be true. Right? So the moles of acid are equal to the moles of base. Well, moles of something is its molarity times its volume, or usually we do this in molarity times liters, but I can substitute volume in here because I'm going to be consistent. So I don't have to have this in liters, I can use milliliters. And if this is for the base, that's the molarity of the base times the volume of the base. So this looks very similar to the dilution formula M1V1 is equal to M2V2, only it's for acids and bases. Because the moles of the acid are equal to the moles of the base, and this times this is moles, this times this is moles. Okay? Again, usually we put liters here, because technically if we want to get moles, it's molarity times liters. But since if both of these are in milliliters, the units will cancel out and you'll be okay. Okay? So good formula to have. Always true at the end point of a titration. The equivalence point is the point in the titration when a stoichiometric amount of reactants have been added. You're trying to add just enough base to neutralize the acid. So if in the first experiment that I showed you, the end point will be achieved when the amount of sodium hydroxide coming from the burette that has been added has been enough to knock out all the HCl. So do the stoichiometry. Acid plus a base makes water and a salt. This is called a neutralization reaction. It's not an equilibrium reaction. It goes all the way to the right. Why? Because you're reacting a strong acid with a strong base. No neutralization. All the way to the right. NaCl is the resulting product. I have salt water. And since it's the salt of a strong acid and a strong base, we already learned that, its pH is 7. Neither of these two things have any acidic properties. Sodium plus 1 has no ability to remove an OH from water. Chloride minus 1 has no ability, or very, very small ability, or really no ability to remove an H from water to make hydroxide. Okay, so neither one of these is acidic. All neutralization reactions go completely to the right. If you were doing the titration of a weak acid by a strong base, then The question is, what would the resulting pH be at the end point? Well, let's take a look at it. During the titration, you're adding external sodium hydroxide from the burette. As soon as it hits the water, it's not going to react with the water because HA, the weak acid that's in the solution, is stronger than water. So it's going to remove a hydrogen to make water and a salt, A-. Okay? When you get to the end point, you've added the correct amount of sodium hydroxide to knock out every bit of the HA. So there's none of this anymore, and it's all over here, right? So I basically, at the end point, have a solution of A-. Well, at the end point, you have a solution of the conjugate base A-. The only thing A- can do is react with water in the hydrolysis reaction, right? This one's neutralization, this one's hydrolysis. Hydrolysis is the reaction with water. Neutralization is the reaction to make water. Okay, so it can turn around, make a little tiny bit of the HA back, and make hydroxide. So our expectation is at the end point, the titration of a weak acid with a strong base should be a little bit basic. Why? Because A- is a little bit basic, and that's the only thing you have in solution. Okay? Here's the note. In the titration of a weak acid by a strong base, the pH at the end point is greater than 7. pH greater than 7. That's all you can say. We're not going to quantify it yet. What about if I do the reverse situation? I do a titration of a weak base by a strong acid. If I do that, the first reaction I have, the strong acid, is basically going to be dumping hydronium ions into solution. How come? Because remember, the strong acid, HCl or nitric acid or something like that, the moment it gets into the water, it decomposes. And this gloms onto a water before you know it, right? Can't even measure how fast that reaction happens. So ultimately, the HCl delivers hydronium. So that's why I don't even have to write HCl here. I can write hydronium because it's the H plus that comes from the HCl on a water. Okay, so what's the first reaction? Neutralization. So it's going to be neutralization first, followed by hydrolysis. So in the neutralization reaction, to get to the end point, I'm adding the HCl, I'm adding the HCl. The HCl is producing hydronium. Hydronium reacts with base stoichiometrically to make the conjugate acid and water. I keep going, I keep going, I keep going. I get closer and closer to the end point. All of a sudden, I run out of this, right? How much hydronium I've added in the form of HCl at the end point, the number of milliliters it takes to get to that special point where the pH is going to change, right? In this case, where the pH is going to drop down, is the point when all of the B that was originally there is gone. So I've added enough of this, the moles of this are now equal to the moles of that. Well, this and this added enough moles of this to react with every little bit of moles of that. They neutralize each other. I use them all up. Now I just have a solution of this and this. Well, water doesn't change the pH. But what about HB+? Well, HB+ is the conjugate acid of B. So it is a little bit acidic. It can react with water to make the base back and a little bit of hydronium. This is the hydrolysis reaction. So at the titration, at the end point, you have a solution of the conjugate acid of the weak base B. So HB can react with water to make B and hydronium. So my expectation is the pH to be less than 7 because I have this species which is a little bit acidic in it. So again, in the titration of a weak base by a strong acid, the pH at the end point is expected to be low, less than 7. Okay, here's an example that we're going to do soup to nuts, right? Which means we're going to do old-fashioned term for every little aspect of it. Okay, so we are going to calculate the pH at the following 5 different values for the titration of a weak acid with a strong base. So we have 0.1 molar. When you say titration of something, that's what goes in the beaker at the bottom, the of something. Titration of 5 milliliters of acetic acid with 10 molar, excuse me, these are both point, right? A little hard to read. These are both point. 1. Okay, 0.1 molar NaOH. So let me just draw the setup for you super quickly. Okay, I have my burette. All right, the burette is filled up with sodium hydroxide. What concentration? 0.1 molar. Okay. Strong base there. What's in the beaker? 50 milliliters. They have to give you the volume of 0.1 molar acetic acid. Good? So, going to calculate the pH at the beginning. That's just going to be before I add any of this. That's just the x squared question. Then I'm going to slowly put it in, and I'm going to calculate the pH at a bunch of different points. Okay? So when you put this in, you get all the any air drops that are in the burette. You shake it and get rid of them. Make sure that everything works correctly, and that the stopcock doesn't leak, and you're ready to go. Oh, you need one more thing in here. You need to monitor the pH during the course of the experiment. So you need to put in a pH electrode, and the pH gives you an electrical signal. So here's the pH meter. All right, so that's what you're expecting. Okay, and this is going to read some numbers. The pH gives you an equilibrium value of the hydroxide ion concentration at any point. If the pH meter is sticking inside a solution and it's stabilized, that's the hydronium, that's a measure of the hydronium ion concentration at equilibrium. As long as it's not moving around, like if you get a reading of 3.7 and it's staying 3.69, 3.7, 3.69, 3.7, 3.69, 3.7, 3.71, that's stable enough, you can take the reading down at 3.7. Okay, so we all agree 0 milliliters is before the titration, before any sodium hydroxide has been added. That's before the end point. Okay, well, first thing we need to do before we can tell where we are in the titration curve is we need to find out what the end point is. So that's a simple calculation that we're going to do in a second. But after we do that first calculation, we then want to see what happens after I add 10 milliliters of the sodium hydroxide, then 25, then 50, then 60. Okay? So here's the steps. Step 1, find the moles of each of the two reactants, which is molarity times volume. Because if we know that, we can figure out when at each of the steps, we can figure out how many moles there are to react in the neutralization reaction. Second thing you're going to take care of. All right, so this is the steps for each of these 5 reactions up here. Then you're going to do the neutralization reaction in moles. Then you're going to change back to molarity, remembering to take into account the dilution factor. Remember, if you're adding, in this case, 10 milliliters of sodium hydroxide to 50 milliliters of the 0.1 molar acetic acid, your volume is no longer 50. Now it's 60 in point 2, in point B. In point C, it's 50 plus 25 is 75. In point D, it's 50 plus 50 is 100. And in point E, is 50 plus 60 is 110. So that total volume is going to be the volume of the solution that you have. So you do need to take into account that as you're adding the acid from the burette, it's going to dilute this solution. Okay, it's going to do a lot more than that, but we do have to take into account that the volume of the solution is going to grow from 50 all the way up to 110 at the very last step. Okay, so always interested in the total volume. Okay, after I change to molarity by taking care of the dilutions, I have to do the hydrolysis reaction. Okay. And the last thing, after the hydrolysis reaction, which is either going to be maybe an x squared question or a buffer question, then find the pH from the x. Okay. All right, very important point, right? the pH at the half equivalence point is equal to the pKa. So if we're lucky enough, right? If we're lucky enough that one of these guys here turns out to be the exact equivalence point, then the math becomes very easy for that particular question. But you still have to do all the other ones. Okay, so next page, super quick review. What's our expectation? If we were doing a strong acid with a strong base, at the end point we'd expect the pH to be 7. If we were doing a weak acid with a strong base, which is what we're doing, we would expect the pH at the end point to be greater than 7. If you were doing a weak base with a strong acid, you'd expect the pH at the end point to be less than 7. These two are probably pretty close to 7. This one might be 8 or 9. This one might be 6 or 5. They're not going to be, 1 or 2 or 12 or 13, but they will be higher and lower. All right, so here we go. Let's read the question, and then I'm going to show you what the diagram looks like. Let me see if I can get the whole thing on the same page. And then these have the answers on it, but I'm going to show you how to do the calculation for all of those guys over there. Okay, so first, what's the question? This is a repeat from the one that was at the beginning. What is the pH at the following points during the titration of 50 milliliters of 0.1 molar acetic acid with 0.1 molar sodium hydroxide at the start of the reaction before any additional sodium hydroxide is added, 0. Then 10 milliliters in. Then 25 milliliters in. Then 50 milliliters in. Then 60 milliliters in. So obviously 50 milliliters looks like it's right either exactly at the equivalence point or a little bit before it, because look, this thing has just taken off. When the pH starts to change dramatically, the highest slope on there, that's your equivalence point. Okay? So the pH meter would barely be moving for the first, 40 milliliters of adding the sodium hydroxide. Then all of a sudden it starts taking off. So you slow down. If you were doing this in lab, you would start moving the stopcock very small and letting one drop come in at a time, and keep it stirring because you want to make sure you don't blow right past it. You want to catch what this point is. You want to get enough data in here. So it looks like we have that data piece. Okay, so the first thing that we need to do is, I gave you the answers here, but if you were doing this on a test, you don't know what the endpoint is. So let's calculate what the endpoint is. Okay, so the way to calculate what the endpoint is the molarity of the acid times the volume of the acid is equal to the molarity of the base times the volume of the base. Let me not be so cavalier about my M's, right? Let me make sure that this guy's a capital M for molarity. All right, so how much acid do I have? Titration, 50 milliliters, 0.1. All right, no need to change for milliliters because the milliliters are going to cancel in a second. You'll see that. That's from right here, 50 and 0.1. What about the base? B is for base. The base is coming from the strong base sodium hydroxide. Its molarity is 0.1, and we don't know what volume it is that's going to be the equivalence point. That's what we're trying to calculate. The volume of sodium hydroxide, the volume of the base that's needed. Okay? Well, obviously, this number is going to be 50 over here, right? Because 50 times 0.1 is equal to 0.1 times 50. But let's do the algebra anyway. VB is equal to 50 milliliters times 0.1. Everything on the left is still on the left. Right? This times this. And this guy is going to come underneath. Okay. This is in molarity. This is in molarity. They cancel out. My answer will come out in milliliters. So the volume of the base needed to reach the equivalence point is 50 milliliters. Okay, that's important. All right, so in my strategy, this is the 50 milliliters. I have to do this question like an x squared question. It's because it's the pH of the acid before any base has come in. I have to do these two like they're buffer questions. Okay, and I have to do, because I'm going to have both the acid and the conjugate base hanging around. And then over here, I'm going to have to do this one like I'm just adding extra sodium hydroxide to a solution of salt water. The amount of the conjugate acid that's around is going to be insignificant. I should say conjugate base that's around isn't going to matter next to sodium hydroxide. So this one is going to turn out to be relatively easy too. Okay, so the ones that are going to have the most work are going to be these two, these three in the middle, especially these two. Okay, so keep that in mind. 50 milliliters is the end point. Okay. Now that's what I did at the top of this page. Monoprotic acid with monoprotic base, yes. We had HAC reacting with sodium hydroxide. Only one proton. Oops, sorry. Only one proton. What's the neutralization reaction? You make water and the salt. In this case, the salt ion is AC minus. The sodium didn't matter. Okay, first one. Before I add any excess sodium hydroxide, I have my acetic acid in water. Okay, so yes, it's a weak acid, so it's going to go to the right to a little degree, to a small degree. So we always have the hydrolysis of it. Basically, the question is, what is the pH of a 0.1 molar solution of acetic acid? Okay, so this guy's going to be AC minus, this guy's going to be H3O plus, because he's donating a proton to water. Okay, 0.1 is what I had in the beginning, right? This is my initial concentration. This is going to be X, this is going to be X. X is going to be small next to 0.1, so I wind up with my classic X squared question. This 1.7 times 10 to the minus 5 is the given equilibrium constant, or Ka, for acetic acid. This is given, right? So you know that because you know Ka is equal to hydronium times acetate over acetic acid. So this is X times X is X squared over the 0.1. Okay, so we've done that a lot of times. That's how I get that. Okay, rearrange, solve for X, take the square root. You'll get the hydronium ion concentration, which is one of the things that X is measuring. It's also the acetate concentration. The hydronium ion concentration is 1.3 times 10 to the minus 3. Take the log of that number, you're going to get negative 2.88. And we know pH is minus the log, so I drop the negative sign and my pH would be 2.88. Okay, so this is the pH after 0 milliliters of sodium hydroxide have been added. That gives you that point right there. So far, all I've been able to draw was my graph and my dot over here. Next one is what happens after 10 milliliters have been added. So that's B here. All right, so these are going to have a fair amount of work. First thing you're going to do is calculate how many moles of each substance you have. After 10 milliliters have been added, so think in your head, how many moles do I have when they're added to the solution, but before they start to react with one another? So if I had 10 milliliters of the solution coming out of the burette, 10 milliliters is 0.01 liters. This one you have to change to liters because we need to get it in moles. Okay? So moles is equal to molarity times volume. 0.1 times 0.01 gives you 0.001, which is 10 to the minus 3. Okay? That's the moles of sodium hydroxide that are coming from the burette. Okay, this one is always going to be the same, right? How much acid do you have? Well, we only had 50 milliliters in the beaker to start with. Its concentration was 0.1. 0.05 times 1 gives me 5 times 10 to the minus 3rd moles of HAC. Now I have these two substances in the beaker. they are going to immediately react with each other. They're not going to react with water because this is a strong acid and a weak base. This strong base and a weak acid. This weak acid is still a lot stronger than water. So why would sodium hydroxide react with water when sodium hydroxide can react with acetic acid? So the first reaction that's going to happen is neutralization. And guys, neutralization goes all the way to the right. Anytime you're able to make water as a product, that's very stable. It's going to go all the way to the right. So the function of the sodium hydroxide, the strong acid, is going to be to remove a hydrogen from acetic acid to make acetate and water. All the way to the right, neutralization. Okay, I'm going to not confuse you with ice tables, because we're not at equilibrium. I'm just going to talk about before the reaction and after the reaction occurs. And all I have is straight stoichiometry. Okay, so one-to-one stoichiometry. So if I put these two things in a beaker and I got 5 of this, look, they both have the same exponent. I've got 5 of this and 1 of this. What's going to happen? Well, out of the 5 of this and 1 of this is the limiting reagent, right? So I'm going to use every bit of it up. It's going to go down to 0. Here, if I use 1 out of the 5, this guy's going down to 4 times 10 to the minus third. Okay, watch the stoichiometry. For every 1 hydroxide that I have, how much acetate do I make? Well, if this goes down to 0, this goes from 0 up to 1. So at equilibrium, I've got this and this. This many moles of HAC and this many moles of AC minus sitting in the beaker. Next step, get their molarity. To get their molarity, I have to remember that I diluted it by 10 milliliters. It's no longer 50 milliliters. Now it's 60 milliliters from 50 plus 10. 60 milliliters is 0.060. Sorry, my dots are hard to see. 0.060, right? 60 out of 1,000. The initial concentration of HAC, okay, I'm using parentheses and the little 0 to, you realize that it didn't come to equilibrium yet. I take my moles, divide it by my volume to get the molarity. Why am I going to need this? Because this is going to be involved in the next step. The next step is the hydrolysis reaction. First neutralization, then take care of the dilution, then hydrolysis. Okay, so we did it for HAC. What about AC minus? Well, AC minus is in the same beaker, the same volume of 60 milliliters. So I have 1 times 10 to the minus third moles in 60 milliliters. Translate the 60 milliliters to liters, that's 0.06. If I do this, I get 1.67 times 10 to the minus third molar AC minus before the hydrolysis happens. All right, now I have a solution with no strong acid and no strong base. So there's no more neutralization that can happen, but I've got the weak acid, acetic acid, and its conjugate base, AC minus, sitting in the same solution, right? Those are the two concentrations. So I have a buffer, okay? When you're at all of the points before you get to the equilibrium point, the solution is buffered. That's why it's going up so slowly. Okay. All right, so let's do, like we always do with buffers, let's do the hydrolysis. I might as well write the hydrolysis the easy way. So write it from the point of view of the acetate. Of the acetic acid. Acetic acid reacts with water to make acetate and hydronium ion. The initial concentrations are 6.67 times 10 to the minus 2 here, and 1.67 times 10 to the minus 2 here. They come right from the section before. We don't care about water, and the hydronium is 0. This equilibrium has to be achieved by going to the right because I have 0 here. I got to fill in that 0. So this guy's going down by x. This guy's going up by x. This guy is also going up by x, right? One of these creates one of these, comes from one of those. At equilibrium, if I subtract off this x here, and I add on this x here, they're going to be so small next to the numbers that you're adding and them subtracting them to, that they're basically going to be these two numbers. So we can ignore the x here because it's small and ignore the x here because it's small. This x we can't ignore. That's the x that we're following, right? It's not small next to 0. So at equilibrium, these are our concentrations. Here's the given Ka value. Ka has to be equal to concentration of acetate times the concentration of hydronium divided by the concentration of acetic acid. Solve for x. X is equal to the hydronium ion concentration. If you do the math, you're going to get 6.79 times 10 to the minus 5. To get the pH, you take the log of this number. It's going to come out to negative 4.17 if you take the log base 10 of it. Then pH is the negative log of hydronium, so we're going to drop the negative sign, so the pH is going to be 4.17. So that's our second data point. Our second data point is the value. The second data point is the value